In the previous video, we explained how to do the basic OSPF configuration, and we managed to establish communication between PC1, PC2, and PC3. We also tested redundancy in case any connectivity link between the routers failed, and we managed to prove that OSPF is truly a very efficient protocol. But in today's video, I will show you how to do the basic configuration and improve the configuration we have from the previous video. So the topics for this video will be three. The first topic will be how to create the router ID or the identification for all routers R1, R2, and R3. The second topic will be adding MD5 security to the OSPF links we have so far. And point number 3 will be improving the network type in order to optimize OSPF's operation. I'm Richard Reyes, CEO of NLinkit. Let's begin. Let's start with point number 1, creating the router ID for R1, R2, and R3. For this router ID creation process, it is necessary to create a loopback interface in MikroTik. This interface must have an IP address, so we are going to write them in the tables for each router to make this easier for us. This is the address. R1's loopback IP is 172.168.255.1/32. R2's loopback IP address will be 172.168.255.2/32. And finally, R3's loopback IP address will be 172.168.255.3/32. So we log into router R1 and we are going to create the loopback interface, which is nothing more than an empty bridge. So we go to bridge plus sign name loopback and OK. Now we are going to configure the loopback interface's IP address. Alright, the next step is to go to routing router ID. We click on the plus sign name RID or router ID underscore R1. And the ID is a 32-bit number. I clarified the notation is similar to that of an IP address, but it is not an IP address. So what we are going to do is copy the loopback's IP address and paste it into the ID. Click OK. OK, we close these windows and continue. The next step is to go to routing OSPF. And here in the instance, in the router ID option, we select RID underscore R1 or router ID underscore R1. We click OK. Then we go to Interface Template. And add the loopback interface. Click OK. We are going to repeat this process on router 2 or R2. We create the loopback interface. Now we are going to configure the loopback interfaces. IP address. It will be 172.168.255.2/32. Now we are going to create the router ID. Name router RID underscore R2 in ID. We are simply going to paste the loopback's IP address. Now we go to the OSPF instance, and in router ID we select RID underscore R2. Then we go to interface templates and add the loopback interface. Alright friends, now we must repeat this process on router 3. We now have our routers R1, R2, and R3, each with its respective router ID. Now back in R1, let's go to the Neighbors tab and explain why it's so important to have this router ID configured on our devices. What happens is that when you have a network like the one shown on screen, OSPF routers start exchanging information from their databases with each other. So, to avoid the proliferation of broadcasts on the network, OSPF elects a designated router so that it is the one managing the orchestra. Knowing who the designated router is, the other routers will send their information to this single router, and not to everyone, and this way the network operation is much more efficient. So, to see this relevant information, let's go to Show Column and add the adjacency. Add the DR or designated router. Also add router ID and also add priority. Click OK. Here we can see that R1 has two adjacencies, one with R2, and it also has another adjacency with R3. In the adjacency with R3, we can see that the designated router is the one with IP address 172.168.3.1, that is R1. And in the adjacency with R2, the designated router has the IP address 172.168.1.1, that is R1. But there is something key to understand here. and that is knowing how to force the election of the designated router at our convenience, since it is suggested that the designated router be the device with the highest hardware performance or the most powerful equipment due to all the hello packets, routes, and other details from all the routers participating in this network or this OSPF environment. So, to have control over who will be the DR or the designated router, we're going to go to the manufacturer's website. Then we click on Support, go to Documentation, and then over here we can type OSPF. Let's search. Okay, here we have all the topics covered by OSPF, but we are going to look for this one here, DR election. Basically, what it tells us here is that the router with the highest priority will become the DR or designated router. Let's enter this router priority link to look for more details. Alright, the priority is a number between 0 and 255, and we see here that by default, Router OS version 7 comes configured with the number 128. With this information, we return to R1 and see that on the link R1 has with R3, the DR is 172.168.3.1, that is R1. Let's go to Interface Templates. Click on Ether 3 to R3 and see that the priority is at 128. Close here and go to R3. In Interface Templates, select Ether 1 to R1 and change the priority to 129. Click OK. Let's return to R1 to disable the instance so the new DR updates. I also disabled the instance in R3. Then I enable the instance in R1 and I'm going to do the same in R3. Returning to R1, let's go to Neighbors and see that the adjacencies are being reestablished. The adjacency with R3 is taking a little while, but it is now reestablished, and the new DR is now the router with IP address 172.168.3.2, that is R3. Let's now return to R3. And leave the priority back at 128. And we're also going to restart the OSPF instance. We return to R1 and do the same. We enable the instance again, both in R1 and R3. Back in R1 and Neighbors, we can see that the adjacency with R3 is in the process of being reestablished. Here we must wait a few seconds, and the adjacency has now reestablished. And we see that the DR is still R3. So what we are going to do now is force OSPF to always choose R1 as the designated router, assuming that R1 is the router with the highest hardware performance in this network we are working with. For this, let's go to Interface Templates. Select Interface Ether 2 to R2. Priority 129. and also go to Ether 3 to R3 priority 129 and click OK. Now we are going to restart the instances on all routers. We disable the instance on R1, we also do it on R2, and finally on R3. Now we are going to enable the instances again on all routers, and here in the OSPF neighbors of R1. The DR for both the instance with R2 and with R3 is always R1. This is due to the change we previously made in the priority. In this way we have reached the end of point number 1, creation of the router ID, and explanation of the designated router. Now let's start with point number 2, adding MD5 security to the OSPF links. So let's go to Interface Templates, select Ether 2 to R2, and we will be working in these 3 boxes here: authentication, auth key, and auth ID. So in authentication, select MD5. In auth key, type the key we want, but let's first disable the hide password to be able to see the characters. In my case, I will use this key nlink_IT. In the auth ID option, type a number. I will leave 255. Another thing I will do is copy the auth key and paste it into a text editor to use it later on the other OSPF routers. OK. I click OK and repeat the same process for the link Ether 3 to R3. Now if we go to neighbors, these adjacencies should automatically drop because we do not have the security configuration set on R2 and R3. Okay, the adjacency with R2 has now terminated. Let's wait for the adjacency with R3 to finish to terminate. Okay, it has finished. What we need to do to re-establish communication is simply add the security part on R2 and also on R3. So we log into R2, go to Interface Templates. Click on Ether 1 to R1 and fill in the data, authentication, MD5. The auth key option. Uncheck hide password and paste the password nlink_IT. And in auth ID, leave 255. Click OK and repeat this process on R3. Alright, click OK, return to R1, and we can see that the adjacencies have been re-established, and the DR or designated router for both links remains R1. Just as we had planned. With this we have finished point number 2. And let's start with our point number 3, which is improving the network type in order to optimize OSPF's operation. Really what we are doing in our topology is making point-to-point links between the routers. For example, R1 has a single link to R2 and also a single link to R3. Meaning that for each router interface it will only encounter a single router, meaning it's a point-to-point link. But the default OSPF configurations in Router OS version 7 come in broadcast mode, meaning as if what you had is something like this graph, meaning that through one router interface you expect to have more than one neighbor. But this is not our case, so let's improve this by logging into R1. Go to Interface Template and enter Ether2 and down to R2. And find the network type defaulted to broadcast. But let's change it to PTP. Click OK. Enter Ether3 to R3. Network type, select PTP. Now log into R2 in Interface Templates, select Ether1 to R1, network type, select PTP, click OK. Go to R3, select PTP, click OK. Alright, now let's restart the instances on R1, R2, and R3. And here in R1, let's go to Neighbors to see how the router adjacencies are re-established. Notice router R2 already came up, but the adjacency with R3 is taking longer than normal. So let's log into R3 to check what's happening. Go to Interface Templates, and here we find the error. The network type is on an option different from PTP. So we correct it. Click OK. Return to R1. And here we can see that the adjacency with R3 has been re-established. Returning to our topology, remember that we already have the basic OSPF configuration done between R1 and R2, as well as between R1 and R3, but we still need to optimize the configuration between R2 and R3. So log into R2, OSPF, Interface Templates, select Ether2 to R3 in network type, select PTP. And these three security options, we're going to fill them in just as we have done on the other interfaces. Click OK and repeat the process on R3. Click OK. Go to Instances and restart the instance here on R3. Now go to R2 and also restart the instance. Then go to Neighbors and let's add the columns we need. DR, adjacency, priority, router ID, and here we can see that the router is no longer wasting hardware resources on electing a designated router since we are working with a point-to-point link. We have seen that all adjacencies between the different routers are working. In this way, we have finished our point number 3, which was improving the network type, but we still need to verify connectivity between the PCs. After all these changes we have made, let's go to the console of PC 1. Open the terminal and test ping to PC 2. It responds correctly. Let's ping PC 3. It's correct. And finally, let's ping towards the internet. And this looks like it's working well. Let's now log into the console of PC 2. From the terminal, test connectivity towards PC 1. It responds well. We can also test ping towards PC 3. We have a positive result. And finally, let's test connectivity towards the internet. And we see that this is working correctly. Let's go to the console of PC 3. And we will perform connectivity tests with PC 1. Let's also test connectivity with PC 2. And the internet. All these tests have been positive. What we are missing is testing the redundancy between R1 and R3. For example, from PC 3 we can do a trace road to PC 1 and find that it does this in 3 hops. This is being done via this link that I am pointing to here. But if this link between R3 and R1 fails, the idea is that OSPF recalculates the route and automatically sends that traffic via the R3-R2 link. Although at first glance it seems like a longer path, it will give us the opportunity to keep our service up while we fix the failure, and this is simply worth gold. So let's go to R3 to break this link it has with R1. Go to IP addresses, and what we will do is disable the IP address so the adjacency breaks. Return to PC 3 and observe that only one packet towards PC 1 was lost, and the service was restored super quickly. PC 2 also continues to respond well, as does the internet connectivity without interruptions. Let's execute the trace road towards PC 1 again. And observe that now we have 4 hops, and the first exit gateway is 172.168.2.1, that is R2. The traffic is now being automatically routed through this link. The adjacency with R1 was lost when we changed the IP address. Alright, let's return to R3. Let's enable the IP address again. And here in neighbors, let's wait a few seconds, and there it is. The adjacency with R1 is up. And if we return to PC3 and execute the trace road towards PC1 again, we can see that again, it's only 3 hops to get from this PC3 to PC1. Meaning, OSPF is choosing the shortest path, and this is working perfectly. PC1, PC2, and the internet respond correctly. Alright friends, we have reached the end of this basic OSPF configuration video tutorial. I hope you liked it, and any questions you can write in the comments box. Don't forget to like and share it. I'll see you in the next video.